simple system with equations similar to a manipulator. So we wrote M Q Q double dot plus CQ Q dot plus G of Q equals tau. Okay, so what we'll do is we'll assume that M of Q is just mass M constant Q double dot plus the C is just a constant, so C Q dot plus G of Q. Let's assume a simple proportional gravity term Q KQ equals F. So you can see the similarity. This is one-dimensional equivalent of the manipulator equation. Now it turns out that this equation is actually the equation of a spring mass system, spring mass damper system. So this is the mass, the damper, and the spring, C K. Then Q is going to be the displacement of the mass, and the force is basically this. So it's a spring mass damper system. So this is a very well studied system, and we can go from this to build our intuition. So let's assume that the force is zero. Okay, there's no force. So essentially, when you're looking at a spring mass damper system, you're looking at what are known as free vibrations of the system. In the free vibration, the form of the equations would be something like this. I'm just going to move the mass down by dividing throughout by the mass. So C divided by M Q dot plus K divided by M Q equals 0. So when people look at this equation, you don't really need three parameters, mass, K, and C, to define it. You can define it with just two numbers. One of those numbers is called the natural frequency, which is the square root of K divided by M. And the second term which people use is the damping constant. So forget that symbol, what it's called. Does anybody know what that Greek symbol is? Yeah, it is called psi. Okay, 2 psi 2 psi omega n equals C divided by M. So by substituting the value for omega n, you can solve for psi. It is going to be C divided by 2 square root K times M. So natural frequency, damping constant. Okay, these things have a physical meaning, as we'll see. The natural frequency, if the damping was equal to 0, then omega n is the natural frequency, the frequency at which the spring mass damper will keep vibrating, just like a simple pendulum has a natural frequency, the time period, which is by the way related to omega n. The spring mass damper system will keep bobbing around the 0 position if there was no damping. Okay, and the damping constant tells you damping is like dissipation because there's a C involved. let's see, sucks out energy from the system, and the damping basically removes energy. So if you start this system from a non-zero Q or displacement, it eventually settles down to zero. Right? So there are different um, values which psi can take. It only depends on the damping constant, something which you can tune. So there are three cases which people look at. One is damping is greater than 1. In this case, C is greater than 2 square root 2 km. This is known as the over damped case. The second one is psi equals 1. Here C equals 2 square root 2 km. This is called the critically damped case. And then we have the third case where the psi is less than 1 or C is less than square root 2 km. It's called underdamped. Okay, so what does this really mean? Well, what you need to do is do a physical experiment. So let's say that this is Q as a function of T. You take the mass, you displace it, either positive side or negative side, doesn't matter. Let's say we displace it on the negative side and let it go. So once you let it go, depending on the damping, you'll get different things. If it was underdamped, then you'll see that it will shoot from zero, it will shoot up and go down and slowly damp, go to zero. This is the underdamped case. If you use an overdamped, if you use a damper which overdamps the system, then you'll see that it will go something like this. So the difference here being that it doesn't bob around zero. It never really goes beyond zero. It always stays below zero because it started below zero in the first place. And then the last case is critically damped. This is the one which is of most interest. So we started here, it'll actually hit zero like so. Okay, so the overdamped case basically gets you to zero, but it takes longer time than it takes for the critical damped case. And then the underdamped case basically shoots up and down over the zero. When we're looking at a control system, we're trying to, let's say that this was a control system, the spring mass damper was our control system. Because there is unwanted forces, those forces are driving the system away from the zero. And our goal is normally to get the system back to zero. So in this situation, what you want to do is you want to get to zero in the fastest possible time without shooting back and forth. So for a good control system, you really want it to be critically damped. You want it to go to zero fast as possible and not show this overshoot like is shown in the underdamped system. So this would be a good control because it gets to zero in the shortest time. Okay. So what we want to do is we want to make the system critically damped because it gets to zero the fastest time. So let's see how to do that. Okay, now I'm going to rewrite the equation. Okay, when you have a dynamical system, the mass, damping, and K is given to you. You cannot change that because that is system properties. In the earlier example, I just tuned the damping because you could, let's say you could tune it. Here you do not have that, you do not have the ability to tune it because that's what the system is. That's what it is. However, you can do whatever you want with the force F. So this is the thing which will help you to do whatever you want. So let's do this. Let's just assume that, so what you're going to do is design F such that the system is critically damped. Okay, in other words, by design, it won't be critically damped, but you can change tune F to get it to be critically damped. So let's assume F equals minus Kp Q minus Kd Q dot. This is known as a proportional because of this piece and derivative control because of this term. It uses Q. So assume that you want to go to Q equals 0. So proportional to Q. And then the derivative is it acts on Q dot. Okay, so that's an assumption. You still don't know what Kp and Kd is. These are design parameters. And we will set those parameters so that the system is critically damped. So here's what we'll do. Substitute 2 in 1. Okay. Now we'll collect all the terms involving Q dot, and Q double dot together. Now this looks like a very similar system like the free vibration system. There's no force because we've eliminated it. Right? We've moved things around. Now if you want this to be critically damped, we know the condition. It's basically right here. So for it to be critically damped, you want to ensure that this term or psi equals 1, which means C and 2 km. C should be equal to 2 square root km. I think I made an error here. This should be, yeah, I made an error. Just fix this. This is 2 square root km. Okay, so we need it to be this, right? You always want to be critically damped. So C is the term in front of Q dot. K is the term in front of Q, and that's what we'll use. So choose Kp, Kd such that the system is critically damped, which means that we take C plus Kd. This is the term which is in front of Q dot. And then we take 2 square root of K times M. K here is K plus Kp. And the M is the same as it is. So this comes here. And then this mass should appear. So if you look at this equation, what you notice is that KD is a design parameter, KP is a design parameter. So we have two free parameters, but we only have one equation. If you deal with such a situation, one parameter is free. You can choose whatever you want. And the other parameter will be determined by the equation. So we have two constants and one equation. So x1 and use equation to compute the second one. Okay, so you can choose either one. Keep anything fixed. So what we'll do is we'll choose. Um, uh, let's say KP is fixed. Okay, KP is fixed. We solve for KD. Fix KP. Solve for KD. So if you look at this equation, if you fix KP and you solve for KD, you first need to square the both sides, right? So that you don't have to deal with that square. Minus C plus 2 square root K. So this is our, sorry, this should be K plus KP times M. So this is our solution. Okay, so as long as KD is this value for the fixed KP, the system is always going to be critically damped. So here is the best way to illustrate this is to look at a simulation. So what I did first was I chose a system with a certain mass Ck, and you know what? Let's just put 0. This is the free. If you put Kp and Kd 0, that means that's free vibration. Okay, so very standard equations. X double dot is whatever I wrote down there. Kp Kd is 0. I start the system with a displacement, a positive displacement of 0.5. And then essentially, I'm just going to do a plot. So let's run this. So this is giving position as a function of time. Starts from 0.5. You can see there's an overshoot. It shoots beyond 0. It goes to negative and then comes down. So this system by design is not critically damped. It's underdamped. That's why it's overshooting. Now what we can do here is we can choose a Kp. I don't know, let's choose 1. And then the Kd essentially comes from the formula I wrote down. Minus C plus 2 square root of K plus Kp times M. Okay? And now let's see what the behavior is. So you see it was critically damped. It never overshoot. But if you see the time it takes for this to reach 0, that's about 2 point, I don't know, 2 point, so it's 2.5 and 5. So maybe about around 4, maybe 3. So it takes 3 seconds for it to go from 0.5 to 0. 3 seconds you might say is too much. How do you change that? Well, what you can do is Kp is a free parameter. Let's just make it 10. And now run this. So remember 3 seconds was what it took. Now it goes down much before 2.5, maybe about 2 seconds. If you still want to make it faster, you just keep increasing Kp. Oh, yeah, so you can see now it's like, I mean, it's spot on. It just goes to 0 immediately. So simple idea to tune a PD control.